Hallo Georg.
Hallo. Stefan, kannst du den Laserpointer hier sehen?
Ich kann eine Maus sehen, aber keinen Laserpointer. Eine Faust.
Ja, den roten Point siehst du nicht.
Nein.
Aber den Highlighted Circle?
Nein.
Ah,
Hallo. Ich sehe
hallo
auch nur eine
Wolfram.
kleine Hand.
Oh, okay. Wie kann ich denn?
Das wird übrigens alles mit aufgezeichnet und landet auch auf dem.
Ja,
Okay.
okay. Ich mache mal den ganzen Screen.
Jetzt sehe ich den Laserpointer.
Wunderbar. Ah, okay. Ihr seht mich?
Ja.
Ja.
Okay, let's start. I'm not sure if last lecture the laser pointer was visible. I apologize if this was not the case. I hope now it is visible to everyone. So let's recap what we did last lecture. We talked about noise and how to quantify it, and we came to the power spectral density with units of watts per hertz, which is like a fundamental representation of noise. In electrical circuits, but it's not very handy to work with a power. In electrical circuits, it's much easier to measure a voltage level. And so we came up with the equivalent concept, which is then the amplitude spectral density, which is measured in volts per root hertz, and it has strange units because what we in reality want to represent is a noise power. And since power is proportional to voltage squared, in all calculations, we have to square this value, then do the operation, and then take the square root again. One example is if we want to compute, for example, from a RMS voltage, a noise voltage, if we want to go to the density, then we could take the correct way and say, okay, we convert this RMS voltage into a power. Then we have to use have to know what the resistor is in the system. Then the power we can divide by the bandwidth. Then we arrive at the spectral density, and then we can take the square root again and compensate for the divide by the resistor, and then we get the amplitude density in volts RMS per root hertz. Of course, there's a shortcut. We can simply take the RMS voltage here and divide by the square root of the bandwidth and arrive, of course, at the same result. Okay, but in order to, sometimes people ask me, okay, when can I add voltages? When do I have to square them before adding and take the square root afterwards? And if it's a noise property, squaring the noise voltages, then doing the linear operation like adding or integrating, and then afterwards taking the square root is always correct. It's like the incoherent way to add signals. Okay, I have to activate this. Okay, so how to measure spectral density? Well, we have discussed already one method to do that. We take our signal, we apply a filter. We can build filters for different frequencies and then map out the complete spectrum if we want. And then whatever comes through the filter, we convert to a power and measure how much power that is. And that's, as I said, is used for very high frequencies where all the other methods actually don't work. Well, more common, of course, is to use an RMS meter. So it's a special type of voltmeter. It often reads true RMS on the label. And then you can simply supply an time varying voltage. And it will give you the RMS value. If you already know that your spectrum is wide, that all frequency components contribute with the same power, you can simply divide by the square root of the bandwidth, which is typically given in the documentation of your RMS meter. Or if you want to map out the spectrum again, you could build different filters centered at different frequencies and measure then for each filter an RMS value and calculate back to the spectrum. The same can be done with an oscilloscope, of course. Modern oscilloscopes have a built-in function to measure the RMS of whatever is on the screen. And like that, you can also determine the noise voltage of a signal. And again, you can use filters to do this then in a spectral dependent way. Well, the most modern and most efficient way to do this is to convert the signal to digital and then calculate the spectrum. So you need an algorithm to go from a time series to a spectral dependence, and that's almost done with a fast Fourier transform, FFT, which then gives you all the frequency components in one go. And so we don't have to apply different filters and measure different voltages. We just get the whole spectrum in one go. And of course, that's much more efficient. So to repeat, if we measure power, we can compute the power spectral density by dividing the power we measure, which is measured for a given bandwidth, by the bandwidth. If we measure a voltage, then we have to divide the voltage by the square root of the bandwidth to get the amplitude spectral density. And if we do this in a computer, we can choose with the algorithm which of the quantities it gives us. Okay, let's talk about noise sources. One really fundamental noise source is the thermal noise, thermisches Widerstandsrauschen in German. It's fundamental, and it's caused by simply the charge carriers in any conductor, basically, that have thermal energy, so they move around. And this, of course, corresponds also to a small electrical signal. The noise power is simply given, or let's say the noise spectral density is given by 4kT, where of course K is the Boltzmann constant and T is the temperature. So you see directly that the power that is actually put into the system by heating it from the outside is converted into an electrical signal. By the way, you cannot use this as an efficient way to generate power because in thermal equilibrium, this does not produce a significant temperature difference that you can use somewhere. You would need a temperature difference to another room where it's colder. So to use this, and then you would probably get the exact same efficiency as with a Carnot process. Okay, if we integrate the spectral density, power spectral density over a given bandwidth, then we get the power in that bandwidth, same thing as we had before, just the other way around. And this power in a given bandwidth, we can of course convert to a voltage simply by taking the square root and adding in the resistor that converts this power to a voltage. And then we can find the equivalent circuit where we have a voltage source which generates this noise signal here and a resistor. So we replace this by that and then can model how the noise of any resistor affects our system. Yeah, well, it's independent of frequency. The frequency dependence that we have here is the bandwidth. Yeah, so if you apply a filter that is only 1 Hertz wide, you get much less noise compared to a situation where you have a filter that's a megahertz wide. But it does not depend if this 1 Hertz wide filter is centered at 10 kilohertz or 100 kilohertz. You will always get the same amount, the same noise power, or the same RMS voltage if you keep the bandwidth the same. It's handy to remember that a 1 kilo ohm resistor produces 4 nanovolts per root hertz. So this means any 1 kilo ohm resistor, if you put a filter behind it with 1 Hertz bandwidth, you get 4 nanovolts of noise, which is a small number. But of course, if you have a larger bandwidth in your system because you want to see fast signals, then this adds up quickly and you get a larger value. If you convert this number, you have to remember that both the bandwidth and the resistor is under the square root. So for a 100 kilo ohm resistor, we don't get 100 times the 4 nanovolts, but 10 times the 4 nanovolts because we have to take the square root. And if we look at the bandwidth of a megahertz, we don't get 1,000,000 times this value, but just 1,000 times because we have also to take the square root of the bandwidth here. Okay. Yeah, white noise spectrum, this means that it's, well, this fixed value. So let's say we have a 100 kilo ohm resistor And we just said that this corresponds to 40 nanovolts per root hertz. We have to take the square root of the 100. This is the level that we see here. Now, if you calculate the spectrum, since this is a random process, you will see frequency components that have a bit more than that and frequency components which have a bit less than that. And the typical way how such a frequency spectrum looks like, if you plot it with logarithmic axis, which is the standard way to do that, is this blue signal that it seems to get larger to larger frequencies. This is not true. It's the same statistics at the large frequencies here than at the small frequencies. It just looks like that it gets larger because here at the large frequencies, the FFT algorithm produces frequency values with equal frequency separation. It's called the resolution bandwidth of your spectrum analyzer. And in this case, we have a resolution bandwidth of maybe a hertz. Yeah, so we get a value for 1, we get a value for 2, we get a value for 3. So these are, we can see the individual values here at the low frequency end. At the high frequency end, where, I mean, here we have 1,000 and here we have 10,000. We have like 10,000 values in a small region of the plot. And those values then explore all the different randomly distributed values that we have in our spectrum. And because there are so many points in between here, there are always a few that are at the extremes. And the more points you count, the more likely it is to find points that have extreme values. And for that reason, it looks like that the values get more extreme here at the high frequencies. But in fact, you can average. You see here per pixel we have many hundreds of data points, and we cannot display them all. So it's a possibility to average over frequency bins with the same width. And then actually you see the reverse. It's the orange signal that here where we have many points, they average actually very nicely to the value that we have calculated. And then here where we have less points, just the averaging is not as efficient, and we simply see noise. Now, if you would repeat this measurement many times and take the average of all those measurements, there again, you have to pay attention that you average in this way by squaring the values, then doing the averaging, then taking the square root. Then it would approach the red line more and more. And after 10,000 measurements, it would just be a perfect line characterizing this noise. Yeah. So a noise process is a statistical process, and we can only describe the average behavior with the numbers that we calculate. And so in each representation that you would measure in the lab, of course, you will see slight deviations from that. Okay, next noise I'd like to talk about is shot noise. We also had this already in the introduction. It's also a fundamental noise. We have no way to avoid that. And it's caused by the charge carriers, for example, through a diode here, that of course have a finite charge, and they arrive when they're registered at statistically distributed arrival times. And so the number of electrons, let's say, that are detected scatters according to Poisson distribution, simply counting statistics. And for that reason, there is an uncertainty in every time bin that we now take to count electrons. And the most sensitive way to measure a current would be to count individual electrons. And if we say, okay, we take values for 1 microsecond, then we would get a count of electrons for each microsecond. And those counts are statistically distributed according to the Poisson distribution. And now we can also think about microscopic currents that still have the same distribution. It's just typically very small noise contribution. So the RMS noise in a current is then given by the square root of 2 times the electron charge times the DC current, and again times the bandwidth at which we observe our signal. Of course, the electron charge is a very small number, and so if you convert the current, or if you multiply the current with electron charge, you get a measure of the number of electrons in a given time interval that arrive or that carry your current. And so you see the counting statistics is built into this formula in this way. So let's have a look at an example. In my scientific life, I often look at signals that come from photodiodes. And the typical current in a photodiode is a microamp. And now if we look at this current noise we just calculated in a 1 Hertz bandwidth, so very small bandwidth, this gives 5.7 times 10 to the minus 13 amperes. This is a very small number. If we put this in relation to the DC current, it's 0.5 ppms approximately. So if we want to be able to detect if we want to detect like 1 million different light levels with our photodiode, then this would be roughly sufficient to that. Or at least we would not be limited by shot noise. 1 Hertz bandwidth means that we can do approximately 1 measurement per second, and this might, of course, not be fast enough. So if we want to be significantly faster, if we want to have a megahertz bandwidth, then this delta F here changes from 1 to 1 million. And so we get 1,000 times, since it's below the square root, we get 1,000 times worse noise performance. And then, of course, we will not be able to distinguish 1 million different levels since we have 500 parts per million noise on this signal. Okay, so just this to illustrate how the noise components or the noise contributions scale with bandwidth. Okay, and then the third very common but not fundamental noise is 1/f noise, also called pink noise or flicker noise. And what I show here is an example from a datasheet of an op-amp. And in the datasheet, you find this noise spectrum. So this is a nicely averaged noise spectrum. You don't see the individual takes, so this is probably averaged over thousands of individual spectra. And so you see that there is a region where the noise is flat, does not depend on frequency, so that's the white noise region. There's a region where the noise rises, and this is typically towards small frequencies, and this is called the 1/f noise region. And then if you approximate them with lines, you can define where these two lines intersect, and that's the 1/f corner. And 10 Hertz is a typical frequency where this 1/f corner occurs. So if you are significantly above that frequency, you don't care about 1/f noise, then you are in the white noise region. If you are below this corner, then you have to take also into account the 1/f noise. Yeah, 1/f noise is a slang term for this kind of noise contribution. It's typically proportional, so the noise spectral density is typically proportional to a function which goes like a constant times to the minus alpha, with alpha somewhere close to 1. And I've seen examples where alpha ranges from 0.5 to maybe 1.5. And all this is called 1/f noise. Accordingly to this, we find a power and amplitude spectral density that goes with the square root of this. And so there, for the alpha equal 1, we find an alpha equal 0.5. In order to specify this, and so now the white noise is easy to specify. We just have to give one number since it does not depend on frequency. In order to specify the 1/f noise, typically what people put in data sheets is if you integrate this noise in a bandwidth from 0.1 Hertz to 10 Hertz. So this is pretty much the region here in the spectrum that is dominated by 1/f noise, and then you convert that into a peak-to-peak voltage using the formula that this is equal to 6 times the RMS voltage. Yeah, and this is what you find in the datasheet of the same op-amp. So you see here the voltage noise given in a noise peak-peak. The two P's here mean peak-peak. And here specified what are the conditions, so from 0.1 to 10 Hertz, and it gives you 0.1 microvolts peak-peak. And well, this is good news if you want to do a measurement and you want to distinguish a million different states, and your signal is approximately a volt, then 0.1 microvolts peak-peak will allow you easily to do that. Okay, now it also specifies the white noise density. It says it's measured at 1 kilohertz. So if we go back, this is here, but I mean, they also provide the spectrum. So you see it's also valid for 100 hertz, and it's still pretty well valid at 20 hertz. And then if you go to smaller frequencies, this is not valid anymore. And so they give 1.8 nanovolts per root hertz. So if you have a megahertz bandwidth, then this converts to 1.8 microvolts RMS noise. And this is, of course, not enough to distinguish a million different states. So you have to take care that this number has a different unit, and you have to take care of the bandwidth with which you operate. Okay, then there's two specifications for the current noise given at two different frequencies. And here, for example, at 200 hertz, we find 1.2 picoampere per root hertz. So that's the again a characteristic feature of this particular op-amp. Now, in general, if we want to combine now different noise sources, we see we have current noise, voltage noise. There might be contributions from 1/f noise and contributions from white noise. So if we want to combine them, we can combine the power spectral densities directly. We can directly add them. And as I've said, if we want to combine amplitude spectral densities, we have to square them, then do the linear operation, and then take the square root again. Simply for the reason that if you add powers, there is law of energy conservation. So they have to add directly. If you add amplitudes, there is no amplitude conservation law. So basically, we have to convert to power first by squaring them. Then we can add them, and then we have to take the square root again to get an amplitude out of that again. Okay, now let's have a look at an op-amp and calculate how much noise we would expect in such an amplifier. So again, we take this ADA 4004 as an example. And what I've drawn here is an inverting amplifier with a gain of 101. No, sorry, it's a non-inverting amplifier with a gain of 101. So here's the input signal. And then the output signal is divided by a factor 1 to 101. And the amplifier keeps the output at a level that is equal to the input, taking this dividing factor into account. So it's 101 times larger than the input. Now, in order to calculate the noise, what we do is we ground all inputs. So this is now connected to ground. And that's why I said inverting amplifier just a moment ago, because if it would have been an inverting amplifier, then here would be the input. Now you see these two resistors then would also form an inverting amplifier. And for the inverting amplifier, we would also connect the input to ground. So the calculation we are doing here applies to both the inverting and the non-inverting amplifier. Okay, now let's go through the components. So we've just seen in the datasheet that the amplifier has 1.8 nanovolts per root hertz voltage noise and 1.2 picoamps per root hertz current noise. And now let's see how this combines with the other components to get us a total noise figure. And the first thing we are looking at is R1. So this resistor here has 100 kilo ohms, and we have already seen that this is 40 nanovolts per root hertz. Now, if the voltage level here goes up and down by 40 nanovolts per root hertz, the amplifier will do whatever necessary to keep its output at the level where it wants it to be. So it will compensate for that. Yeah, so if this goes down, this has to go up. And so we get a direct copy of this noise onto our output signal. R2, this resistor here, it's 1 kilo ohm, and we have already seen this is 4 nanovolts per root hertz. Now you would think, okay, this resistor is 100 times smaller, it has 10 times less noise. So this is probably not it's not contributing a lot. But if you have a look, this is at the point where in an inverting amplifier where the input would be. So if we have this voltage going up and down, then what the amplifier does is it amplifies it by a factor 100. So on the output, the noise that we have here appears 100 times larger. So what we have to calculate, now we calculate all noise contributions referring to the output. What we have to calculate is the noise from here, 4 nanovolts per root hertz times 100. And so we get 400 nanovolts per root hertz, which is more than actually from the larger resistor, 10 times more. Okay, then we have the direct voltage noise of the amplifier, so the 1.8 nanovolts per root hertz. And this is also a signal that is on the input. If we look at this as a non-inverting amplifier, then the voltage signal that we have here is an input signal, so it gets amplified by a factor 100 again. And so we have to count 1.8 nanovolts per root hertz times 100, 180 nanovolts per root hertz. And then the last contribution is the current noise. Yeah, so there is a current noise on this input here. We have to take, there's a fluctuating current going in and out of this input. It's very small, it's picoamps per root hertz. But what happens is we connect now resistors to this input. Since there are no resistors in this particular schematic, at this input we can ignore the current noise for this input. But here we have resistors, and so the current is converted to a voltage in the resistor. And so let's calculate what that does. Now remember, we are in a situation where all inputs are connected to ground, and of course the output is also at 0 volts potential. So what we have in effect now is a current that is connected through this resistor to ground and through this resistor to ground. So it's a parallel configuration of two resistors. And in a parallel configuration, always the smaller one dominates. And so this resistor here converts our current to a voltage. And since this is again at the input, we have to multiply with 100. So what we have to calculate is the 1.2 picoamps per root hertz times 1 kilo ohms, this, times 100. So it gives us 120 nanovolts per root hertz. And now in order to calculate the total power, we square all those contributions, the 40 nanovolts per root hertz from this resistor, the 400 from this resistor, the 180 from the internal voltage noise, and the 120 from the internal current noise. And then this gives us 456 nanovolts per root hertz. Okay, so this amplifier, if you look into the data sheet, the first thing they say, this is a super low noise amplifier with 1.8 nanovolts per root hertz. And now we find a figure here which is 400 something. And of course, the reason why this is so large is that we have a large amplification factor. And if we now calculate back to the input, we find 4.65 nanovolts per root hertz. Yeah, so what does that mean? If we want to measure a small signal, let's say a microvolt, signal that goes up and down, and we have a few hertz bandwidth, then this noise figure would be sufficient to register such a small signal. Yeah, so we get a few tens of nanovolts of noise, which is a small number. It's good performance. But we also see this number could be smaller. Yeah, it could be as small as 1.8 nanovolts per hertz. That's the like fundamental voltage input noise of this amplifier. And in order to make it smaller, we have only one thing we could change, and this is the value of those resistors. So if we make those resistors smaller, let's say we make it a factor of 10 smaller, then we would reduce those noise contributions by a factor square root of 10, and this would bring us already much closer to the 1.8 nanovolts per root hertz. If we further reduce those resistors, several things happen. The op-amp can deliver like plus minus 10 milliamps. And so if we go to something smaller than a kilo ohm, then we might be limited by the current that the amplifier can produce. There's another disadvantage by reducing those resistors, and this is power consumption. If we go to like a 1 kilo ohm and 10 ohm configuration here, we would get really low noise, but we would also, a large current would flow all the time through those resistors, which means that we cannot drive as much current to whatever comes after our amplifier. And it means it's power that our amplifier dissipates all the time. Yeah, and so if you want to build a really, really low power amplifier, like, I mean, for your smartphone, you wouldn't want a signal that drains your battery all the time. Then it's a disadvantage to go to really, really small resistor values. Yeah, so this is a trade-off that you have to live with if you build a fundamental physics experiment where power doesn't matter. Then you can, of course, go to the smallest resistors that are still practical given the output current capability of your amplifier. If you have to build like 1 million of those in really small space, then power might be a concern. And then you have to optimize for power as well. And of course, if you are an application engineer and you want to build something that is battery operated, then going to the smallest resistor values is, of course, also not an option. Okay, this concludes the section about noise. Are there questions to this section? Okay, I don't see any. I will stay in the Zoom room also a bit after the lecture. So if you have questions, you can also ask them then. Okay, so we move on to the next subject, and that's analog to digital and digital to analog converters. And well, basically they are the interfaces between digital logic and analog signals. If you want to get an analog signal into the digital domain, you need an analog to digital converter. And if you want to get out of the digital domain into analog signals, you need a digital to analog converter. So ADCs, analog to digital converters, AD converters, convert analog signals, of course, into a representation of an integer value. DACs, digital to analog converters, do the opposite. They convert a digital value to an analog voltage. Typically, a voltage could also be a current. The digitized values then, of course, can be processed with whatever digital logic you want to put in between here. And this will be the subject of next semester electronics for physicists. Well, there are many many possible digital things you can have in between here, like microprocessors, special embedded processors, signal processors. There are special processors that are optimized to handle signals, for example, in mobile phones or in cameras. If you want to process a lot of picture data, you can make processors that are especially efficient in doing that. It could also be gate logic. So you can design an algorithm simply by logic gates. And then this is typically implemented in a field programmable gate array. So that's a special chip where you can program the logic that you want to be applied. Or if you then want to go into like a large series, or you have very special requirements, you can design a piece of silicon that actually does exactly what you want to do. And then that's an application-specific integrated circuit, an ASIC. Okay. Typically, ADCs and DACs used a fixed, fixed sampling rate, German Abtastrate, we will call it FSR. And this simply determines how often in time the values are converted between analog and digital. And so what we do is we go from a time continuous analog signal to a series of time discrete digital values. Yeah, so there's two kinds of digitization that happen. One is in time. Yeah, so we chop our signal into time segments, and for each time segment we get one number. And the second is that the number has a limited resolution. So also we quantize in the possible values that such a state can have. Okay, so let's first have a look at time discrete data. And what you have to know there's the Nyquist theorem, which basically says that time discrete signals with a sampling rate of FSR can represent signal frequencies up to half of that sampling rate. Okay. And then a digital signal processing circuit typically looks like that you have an input filter in order to suppress frequencies that can actually not be converted, so that are larger than half the sampling rate. Then you digitize them. You do in your logic whatever you want to do. In this example, we simply copy them to the output. They are then converted to analog signals again, and then on the output, you typically have again an analog filter to reconstruct the signal. So here is an example that the blue curve is the analog input signal. And then if we simply copy the digitized values to the DAC, then an ideal DAC would produce this yellow curve. So after one sampling rate, after one sampling time, so 1 over the sampling rate, you would get the first value. So there's a small time delay here. And then you see that the yellow values follow the analog input signals in steps, of course. Yes, and then what the output filter does is it smooths those square pulses that the ideal DAC would produce to make it look a little bit more like the analog signal that we had on the input. And then this is called a reconstruction filter because it reconstructs how the analog signal actually looked like. Okay, it's important to know the time resolution that you need for your application. The best case is if you have oversampling. So what I've done here, I showed again blue the input signal, and then in between you see the yellow steps. These are quite a lot for this one period. And then in green you see the reconstructed signal, and it looks pretty much exactly like the input signal. Yeah, so by digitizing it in very, very fine steps in time, we get a nice representation of our input signal. Now, if we approach more and more the Nyquist limit, so at a sampling rate that is 4 times the signal frequency, so this is not quite the Nyquist limit yet. And what I've done here is I shifted the output signals in time so that they are easier to compare with the input signal. Keep in mind, in reality, there is a time offset between those. Okay, but if you shift them, it's easier to compare. So you see we get like an input signal digitized at this point. So over this time, the output has a fixed value, and then the reconstruction filter produces something that still looks approximately like our input signal. But you see, this is already, it changes how the signal looks like. Now, if you are really at the Nyquist limit, then you have to be lucky that the sampling times are actually where the amplitude is high. You could also be unlucky and sample here in the where the signal is always 0, and then you will get 0 output. So operating at the Nyquist limit, this is a theoretical limit. It's not recommended at all. And then what you get, well, is this basically square wave that with a reconstruction filter then can be made to look slightly similar to your input signal. So for a real application, I would not recommend ever to go to the Nyquist limit, half the Nyquist limit. So the sampling rate is at least 4 times your signal is, I would say, the practical limit. And if you can afford to sample faster than that, that's typically an advantage. So if you design a system, I would say sample at least 10 times faster than the signal components you are interested in. Yeah, what happens if we do not do what I just said and simply sample at a really, really low rate? And here you see you have a sinusoidal signal, and we sample now here and then here and then here and then here and then here, and we are completely blind to the cycles that happen in between. What we see are the values at the sample times, and then of course the reconstructed signal looks completely different. It has a completely different frequency than our input signal. That's called aliasing. And so signal frequencies that are much faster than our sampling rate, we can simply not represent in the digital domain. And this actually leads then to really a mismeasurement of the characteristics of this signal. And in order to avoid that this happens, you typically have an input filter that suppresses all frequency components for which aliasing could happen. Okay, now this was the time discretization, and the next step then is the amplitude resolution, or the quantization of amplitude values. And well, the ideal analog to a digital converter gives you for each sampling period an output value that is like the closest approximation of your input. And so if we have a sine wave again as an input signal, then you see this yellow digital values now for a 3-bit ADC. So it can have 8 different values. That, for example, here this red dot is closest to this number. And then the red dot directly after it is also closest to that number, so it doesn't change between these two sampling periods here. Also, all the ones up here, they are all represented by the same number, because that's the closest approximation that a 3-bit ADC can give to that signal. Yeah. And so the difference between the input signal and the representation as a digital number is called the quantization error. And they can be significant if you have a low bit resolution. Now, of course, you can buy ADCs with much higher resolution. For example, if we have 8 bits, then already with the resolution of my screen here, the signal looks much nicer and we get much smaller digitization errors. Yeah, we have the number of distinguishable levels is 2 to the n. So for n equals 8 bits, we get 256 different levels. The full scale is defined as the difference between the largest and the smallest voltage we can represent. And then we can compute the level spacing, and this is then the least significant bit. And the voltage of the least significant bit is simply the full scale divided by the number of distinguishable levels. Yeah, and of course, this is a measure on how large our quantization error will be. Okay, let's take a break and we continue then quarter 2. So thank you for the moment. Yeah, okay, let's continue. There is one more feature I'd like to mention here. In addition to the quantization error that we get because there's limited resolution, there's one more error that you can have. And this is, imagine that the time at which the sampling happens jitters, so that it's not always the same time, but some of those points are taken a bit earlier, some of the points are taken a bit later. And then you end up, for example, here on the slope of the signal at a different level. And then also this time jitter is converted into an error of the value that is digitized. So this is, again, one more component that contributes to the digitization error. And depending on how fast your signal is, this can be a dominant effect. Okay. Yeah, let's have a look at the spectrum. So the quantization noise for a typical system is has a frequency dependence that is almost white, as you can see here. So what I did is I simulated a signal of 1 volt RMS, and then digitized it artificially. So generated the output that a perfect analog to digital converter would produce, and then calculated the spectrum of this output. And then you see, of course, the higher the bit resolution, the smaller this noise that accompanies the peak here of the signal becomes. And now there are different different methods how to measure that. We have one scale here at in volt per root hertz. So, and then you can see that, for example, for this 40 kilohertz sampling rate that we have in this example, we have something less than a nanovolt per root hertz for a 24-bit ADC. So this is a really, really small noise level, and in reality, the noise will be larger. But it's clear that if you have, for example, a 12-bit ADC, the quantization noise alone will make this contribution. And unless you increase the bit number, you will not be better than this level. Yeah, so 12 bits then gives you something like 10 to the minus 6 volts per root hertz, which again means that in a second, you can distinguish like 1 million different states. Another common way to specify the noise is the signal-to-noise ratio, also often given in decibels. And the signal-to-noise ratio is simply calculated by the RMS voltage of the signal. In this case, it's 1 volt RMS divided by the integrated RMS voltage. So you integrate the whole spectrum except for the signal peak of all the noise that is in this case generated by quantization errors. And well, yeah, really, really high resolution ADCs go like have more than 100 dB signal to noise ratio. And if you go to smaller resolutions, then it's maybe only 40 or 60 decibels. Okay. Now, in order to get into the right, to explain analog to digital conversion, it's beneficial if we first explain digital to analog conversion. And the simplest DAC is pulse width modulation. So imagine we have two reference voltages, U minus and U plus, and we have a very simple system that can connect our output either to the minus reference voltage or to the plus reference voltage. This could be plus minus 10 volts or 0 volts and 5 volts if you have a more modern electronic design. And then we can generate different output voltages simply by changing the timing on how long our output is connected to the plus voltage and how long it's connected to the minus voltage. So the average output voltage that we get then is the plus voltage value times the relative time it's connected to plus the minus reference voltage, and then we have to subtract from the pulse time the total time and divide by the total time to get the fraction to which it's connected to the minus reference voltage. So if we have a 10% pulse ratio, then we get 0.1 times the plus voltage plus 0.9 times the minus voltage, simply like that. And if you want to change this average voltage, we simply have to change the timing when the switching from plus to minus happens inside this pulse. And then typically the pulse duration is kept constant. With this method, we can generate any voltage between U plus and U minus. And of course, we don't want this to be like a pulse train in our signal, and it's possible to smooth it with a low-pass filter afterwards. Pulse width modulation is typically used in many very different processes, typically if you have large power, because switching on and off, for example, a stove or a light, can be done very efficiently, either with a mechanical relay or with a field effect transistor. And you have very, very small loss in the element that switches, because if it's switched off, there is zero current, so there is no dissipation. If it's switched on, a modern transistor can have a very small internal resistance, so there's also a small dissipation of power. And imagine if you want to generate something in between, then you always have to dissipate power in your amplifier. And this can be avoided if you use pulse width modulation. In modern audio amplifiers, the same thing is used. So if you want to drive a large speaker, you need a significant amount of power, hundreds of watts. And by using such a pulse train and filtering it afterwards, you can also generate a nice audio signal. And for example, in your cooking stove, what is done when you change the heat, yeah, you have the levels from 1 to 9 typically, and all that this changes is the time for which the pulse is on. So there's a direct correlation between the time that's on and the setting on your stove. And that's all that it does. And since since heat is very slow to change, you actually don't really see in the end result that this is actually pulsed operation of heat transfer. Okay, so if we talk about generating an audio signal, here again an example that is a sine wave, then when we want to generate a large voltage here in the peak, we have to have the pulses to be mostly on. If we want to generate a low voltage here in the valley, the pulses are mostly off. And of course, in between, in order to generate something neutral, they are on and off for the same time. And then, of course, this pulse train is not a nice signal. If you would put this directly to a speaker, this would sound terrible. And you have to smooth it. The orange curve, there I've used a filter where the time constant is equal to the pulse duration period, T0. And then you see, okay, this looks approximately like a sine wave, but there are still large artifacts from the switching. You see this goes up and down like a comb all the way through the signal. And then if you want a smoother signal, you can, for example, use a filter with 10 times larger time constant. You see there's a time delay if we go to the green filter here, but the signal becomes much smoother and almost looks like a nice analog representation of our sine wave. And so this way is like the simplest conversion between a digital controlled signal and an analog word that is actually used. A different method to generate an analog voltage is a string DAC. And what we do here is we take again a positive and a negative reference voltage. And then we have a string of resistors that acts like a large multi-step voltage divider. If they all have the same value, then we get equidistant voltage levels at the different points here. And then we simply have to connect our output to the value that we want. For this 3-bit DAC, there are 8 different values. And one particularity that you see here is that we can generate 0. So this is connected to the minus the reference voltage. Let's say this is ground. So we can produce 0 output. Our 0 digital code produces 0 output voltage. Our 111 digital code produces not exactly the plus reference voltage, but is removed by 1 step. In order to represent the reference voltage, the plus reference voltage, we would need 1 more bit. And typically this is omitted because we don't want to build a digital system which just carries 1 more bit in order to just get this 1 more level. If it's only 8 levels, this looks like significant, but of course, if you have a 20-bit DAC, then it's only 1 part in a million that you lose here. But this is a typical way to scale the output between the digital values and the analog voltages. Okay, particularities of the string DAC is that it's guaranteed monotonous, which means that if we switch to 1 level higher, we are guaranteed to get a voltage increase because we divide this voltage in 1 go, and every resistor has a voltage gap. This is an advantage in some applications. It's relatively easy to implement and can have a low power consumption. But the disadvantages are that it's low resolution because you need 2 to the n resistors and 2 to the n switches. And if n gets large, then you have exponentially many components that you need. And if the resistors are not all the same, you can get easily linearity errors. A more clever design is one we have already talked about briefly. And this is the adder. So we can configure a digital adder in a way that it reproduces, converts a digital number, an analog adder, that it converts a digital number to an analog voltage. And the trick here is that we scale the resistors in this adder in a particular way, such that we have a basic resistance value of R, and then and this is the least significant bit, and then every higher bit gets a resistor that is divided by a factor 2. So this is R half, R4, and so on until the most significant bit is R divided by 2 to the n minus 1. And then in the feedback of our amplifier, we use a resistor that is R divided by 2 to the n. And so now what happens if we only switch on this switch? Then we generate a current here that is given by the reference voltage. Remember, for an op-amp circuit, the 2 voltages here are the same. So the potential at this point is the minus reference voltage. So the current that flows here is given by the difference between plus and minus reference voltage divided by the resistor. And then this current is again converted to a voltage using this resistor. So what we get is an output voltage that is, we take as a reference the minus reference voltage and then times this full scale, the difference between the minus and plus reference voltages scaled with those resistors. And the way those resistors are chosen is that this gives us just 1/2 of the full scale. Okay, and then we go through all the other resistors till the least significant bit, where we get a contribution to the output voltage that is scaled by R divided by 2 to the n divided by R. So we get the full scale divided down by 2 to the n. So this is the least significant bit voltage. Okay, and now we can simply use the superposition law that if we have a combination of the switches active, then we get the sum of those. And so what we get as an output voltage is the full scale. Okay, now we take the minus reference voltage as ground. That's easier to write down the formulas. We get the full scale divided by 2 to the n, so the least significant bit voltage, times this sum of binary values times 2 to the n, which gives us, of course, exactly the representation that we want. If all bits are 0, again, we get voltage equals 0. If all bits are 1, we get almost full scale minus 1 least significant bit voltage. Okay, this has the large advantage that we do not need exponential many components. If we go from 8 bits to 10 bits, we simply have to add 2 resistors here and not going from 256 to 1024 components, like 4 times more effort. And this, of course, is a significant advantage of this method, that we can get to a higher resolution without building millions of components into our system. A disadvantage is that the resistor values here have to change by orders of magnitude if we want high resolution. Yeah, so we start with some value R that we can choose. And then if we have a 10-bit DAC, which is not really high resolution yet, then this resistor here has to be 1,000 times smaller. If we want a 20-bit DAC, it has to be 1,000,000 times smaller, which means that we have to have resistor values in our system that change by 6 orders of magnitude. And as we've seen, large resistors produce a lot of noise, and so that's not ideal to build a nice system. And there is a really clever trick to avoid that. So to combine the advantages of like stages where we don't have exponentially many components, but by keeping the system in a way that we don't need orders of magnitude different resistors. It's called the R2R network. And it's really nice design. It's my favorite way to generate analog values from digital values. And one way this is special is that we finally have a really good application for the Thevenin theorem, which was in one of the first lectures. And so here you see the schematic of a 3-bit R2R network. And so, of course, it's named by the resistor values that can occur. And in order to analyze what's going on here, it's best to look at this subcircuit here first and calculate the voltage that we can have at the output of this subcircuit. And we call this voltage 0 because it's generated by bit 0. And so what we have here, it's really simple. If the bit is 0, then this is connected to ground. This is connected to ground. The 2 resistors are in parallel. So what we have in the end is an 1 R resistor connecting this point to ground. And this tells us already what the resistor in our Thevenin form of that circuit has to be. It has to be 1R. If we connect this now to 8 volts, then we have 2 equal resistors, 1 to ground. So this means we halve the 8 volts and get here 4 volts of voltage. So the output voltage has to be whatever the bit value is, 1 or 0, times 8 volts divided by 2, so times 4 volts. So we know that we can replace all that with a voltage source that has, depending on bit 0, either 0 volts or 4 volts, and a resistor that must be of value R. Now, the next step of this circuit is made in a way that we have again 1R, and these 2 R's together combine to be 2R. And so what we had here repeats. Yeah, so we have 2R connected to this voltage, and then again a 2R resistor that connects us either to ground or to 8 volts. Okay, now what happens if bit 1 is connected to ground? Then again, we have a voltage divider that gives us half of what we had here at this point. So this is written down here. The voltage at the output of subcircuit 1 is half the voltage that we had in subcircuit 0. And then what happens if we have an 8 volt signal here and ground here? Then we divide down the 8 volts and we get bit 1 times 8 volts over 2. What I've used here is the superposition method of analyzing a circuit. Yeah, this was also something we had in one of the first lectures. You remember, if we have different sources in our signal, our system, it's valid to have all sources being equal to 0, except for 1, then calculate what the output is, and then have another source activated on all others being connections to 0, and calculate what that voltage then is, and then add all the superpose all those voltages. And that's what I do here. Yeah? So if this is 0 and this is on, we get half of that voltage. That's written down here. If this is 0 and this is on, then we get half of the 8 volts. This is written down here. And bit 1 controls if this is actually active or not. Okay, so putting this together, half of that one gives us bit 0 times 2 volts and plus bit 1 times 4 volts, because 8 over 2. And okay, this already looks like that we can construct such a binary series. And of course, in the next step, what happens again is that if this is 0 and this is enabled, we get half of the voltage that we had before. So again, the voltage after step 2 is half the voltage of step 1. And plus, of course, if this is 0 and this is enabled, we get one more copy of 8 volts divided by 2. So in the end, we get bit 0 times 1 volts plus bit 1 times 2 volts plus bit 3 times 4 volts. Exactly what we want in order to generate a voltage according to our binary values. Yeah, and the power of this method lies in the fact that each stage halves the voltage of the stage before, just by its construction, by clever choosing the values of those resistors. And because of that, we don't need a large variety of resistors, since each stage automatically divides down what was in the stages before. Okay, and in order to make a system out of it, then we take the output of this R2 ladder and feed it in an inverting amplifier, where with a feedback resistor, we convert that to a nice voltage. Yeah, which then of course gives us an output voltage, which is a minus sign here because it's an inverting amplifier, times a gain factor, which we can choose by choosing this feedback resistor with respect to the resistors in the R2 ladder. And then, of course, again, the minus reference voltage plus the full scale divided by 2n, so least significant bit voltage, and then times the binary value. This is, of course, used in many systems. One particular DAC that I work with then combines it with other topologies. So it has a 14-bit R2R ladder. So that's the part we just discussed. And then the last 6 bits are directly decoded. And with this together, you get 20-bit resolution. So this means more than 1 million voltage levels, or 1 part per million resolution. You can choose those values 1 million times per second. So you have a time constant of a microsecond. And in the internal noise, something like 7.5 nanovolts per hertz. And what is special about this DAC is that it has a very small temperature drift. So it changes its value only by 0.05 ppms if you change the temperature by 1 degree. So this is stable and low noise, and we use this to generate magnetic fields in our precision experiments. Okay, now we can come to ADCs. And there is direct correspondence to the string DAC is the flash ADC. And so what we do here is we have an input voltage, and then again we need a plus and a minus reference voltage. And the reference voltage is divided down into n steps by a network of n resistors. And then we simply use comparators, so basically op-amps, that tell us if the voltage that we have on the input here is larger or smaller than the reference voltage that we have generated here. And so for each of these steps, we get, so I don't know, if this is 10 volts, this is 0 volts, and we have a 5 volt input voltage, then all the comparators that are above 5 volts will say 0, and all the comparators that are below 5 volt will say 1. And then we need some digital logic that converts this like a bar graph of digital values into a digital number. But that's can be easily done with some gates. And well, the advantage of such a flash ADC is that it can have really high sampling rates. Now you see everything works in parallel. The voltage comes in, this is static, divided down. All those comparators can be fast analog circuits. They compare the input voltage with the static reference voltage, give an output, and then there is a digital system that simply samples this those values and converts it to a digital number. There is a very, very short delay. So the signals are virtually instantaneously converted. And that's why it's called a flash ADC. Yeah, it's very parallel, which makes it fast, but it also means a large power consumption because you need many, many, many components. And of course, the number of components scales exponentially with the amplitude resolution. And yeah, I mean, typical sampling rates that you can have for 12-bit flash ADC. 12-bit is already really high resolution for flash ADC because you need 4096 comparators. you can go to like to a gigahertz, and if you go down to 3-bit, you can have many tens of gigahertz sampling rate. Now there's a more modern version of the flash ADC, and this is a pipelined ADC. This works like that you have basically divided down into different stages. And in each stage, you have an input voltage that is converted by the flash ADC into a digital value. And then directly a DAC generates the analog representation of the digital value. And then this is subtracted from the input signal. And then this goes to the next stage. And you can imagine that there is a gain factor here in this amplifier, so that the next stage can in principle look exactly the same as this one. And then in each stage, you can convert, you can like, first of all, get like the rough digitization, get a few bits of resolution, and then you subtract this from the signal and amplify it. And what's left is like the digitization error of the first stage. And then you send this through a second stage where you determine how large that was in a given approximation. You subtract that from the signal again, so you get the digitization error of stages 1 and 2 combined. It's then the input to stage 3. And so this is much closer to your signal. You can amplify this again and do one more step. And then what remains, you can feed into a flash ADC. The advantage of this ADC method is that you can, that each stage, for example, can determine like 3 bits of resolution. This keeps the number of components that in each stage are necessary in check. It's not really a lot that you need then. And you can combine stages, so you get 3 bits here, 3 bits here, 3 bits here, and then in the flash ADC in the end, let's say you determine another 3 bits, and then in the end you have a 12-bit ADC. And so the components, the number of components that you need, they don't scale exponentially anymore with the resolution, but linearly. And this makes, of course, makes it much easier to determine the signals. What you lose, of course, is a bit of this instantaneous conversion that you have with a flash ADC. So if you need the digital answer directly, this is the best thing you can do. In this setup, typically this is timed in a way that the stages, that the signal moves through the stages. And while this stage operates on a signal, this one here already takes the new signals into account. So you, in these 4 stages, you approximately, it takes like 4 times as long to get the signal out than it would be if it would be a simple flash ADC. But still, I mean, they're very fast, and it's like the method of choice for very high frequency digitization signals. Okay, yeah, let's come to a different kind of ADC, and this is now used if you want for significantly smaller frequencies but higher resolution. It's a successive approximation ADC, and this works in stages. The first stage is that this switch here is closed and this switch is open. And then you see we have an RC circuit here that charges the capacitor to the voltage that we have on the input. And then this switch is opened, and what the capacitor does is it stores the voltage that we have on the input. So while this switch is open, if there is any change on the input, we are blind to it. And now what the ADC does is it determines the voltage that we have stored in the capacitor. It's also called a sample and hold circuit. So again, we use a comparator, and here we have a DAC. And now what the logic does is it generates like the mid-range voltage with the DAC. And then the comparator tells us if the voltage that we have here, of course, switch 2 is closed, if the voltage that we have here is larger or smaller than the middle. Yeah. And then we can do, depending on the answer, we can do one more, the next step and say, okay, if it was smaller, then let's go to 1/4. Then the comparator tells us again, the voltage we are looking for is larger or smaller than what we generated. And like that, the logic can successively approximate the voltage that is stored here. So what it basically does is it performs a binary search. And so in order to gain n bits, it has to do n cycles of generating a voltage here and reading out the comparator. And this can be very fast. So what you need is a good DAC and a good comparator, and the rest is just digital logic. And so if you want to do 24 bits of resolution, typical sampling rates are on the order of 100 kilohertz. If you want to do 16 bits, you can get several megahertz. 10 bits, several hundreds of megahertz. And so the advantages of a successive approximation ADC is that it has a fixed conversion time. So this program to search for the correct value needs some time, and then the answer is there. The latency is low, it's just one conversion time. And so for that reason, it's suitable also for fast servo controllers where you want to measure a voltage, you want to react to it, then measure again, react to it again, and so on. Yeah, on the other hand, delta sigma ADCs work in a completely different way. What we do here is we have the input voltage on a difference amplifier. And the difference amplifier compares it to the output of a 1-bit DAC. And this 1-bit DAC can either generate the plus or minus the reference voltage. So it's not really a DAC, it's just connecting this line here to either plus or minus the reference voltage. And then the output of this difference here, so that's why it's called delta, is integrated. So a capacitor is charged with it. The integrator is like a sum, so that's why sigma. And then it's a comparator that detects if this integrated value exceeds a certain value. And if it goes too much up, then it tells the DAC to switch to the minus reference voltage. And if it goes too much down, it tells the DAC to switch to plus the reference voltage. And what this does is it generates a pulse train. So what we have here is a 1-bit representation of our input signal with pulses that correspond to plus and minus the reference voltage. And this signal for a first order delta sigma ADC, as is shown here, is exactly the same thing as a pulse width modulated signal. So the density of high pulses is proportional to our input voltage. And then, of course, we can have a digital low-pass filter that reconstructs our signal. And then what is done is in this low-pass filter, which is typically done in different stages, you also increase the number of bits in the digital representation. So it goes in as a very fast train of 1-bit pulses, and it comes out as a much slower train of digital numbers that then have higher bit resolution. Yeah, typically delta sigma ADCs, and despite the fact that the signal starts as a 1-bit representation, they have the highest bit resolutions in the end after this digital low-pass filter. Up to 32 bits are commercially available for sampling rates, let's say up to 3 kilohertz or so. And then 24 bits, still very high resolution. You can get up to 4 megahertz, and 16 bits you can get to several hundreds of megahertz. Because we need this digital filter, the sigma delta ADC has a large conversion delay. We've seen this already in the example with the here, that if we have a pulse train and we use in this case an analog filter to regenerate our nice signal, it's mathematically exactly the same in the sigma delta ADC, where we have this pulse train, and you see already here we have the high density of pulses, but the filter gets to a high value only here, so there has to be a certain time delay, and this makes it typically not suitable for fast. Oh, sorry, I'm going to the wrong direction. Not suitable for fast feedback, for example. So the time it takes, the latency, the time it takes that the digital logic here is aware of a signal change can be substantial. Okay, let's have a look what happens with the signals inside a delta sigma ADC. So what I've shown here is an input signal that looks like a sine wave. And what we have here is the integrator. And here at 0, and I have to say the reference voltages are plus and minus 1 volts. And so here at 0, what happens is that we switch, for example, to plus 1 volts. Then the difference between our input voltage and our reference voltage is 1 volt. And so the integrator charges up with 1 volt signal, integrates this 1 volt signal. Then as soon as we hit the threshold, we switch to minus 1 volt. And then it goes from the value that it had with the same slope down until we had hit the negative threshold. Then we switch again to plus 1 volt and so on. Since the input signal is at 0, the slopes of this plus and minus integrating happens, plus and minus integration happens with the same slope. For that reason, we hit the thresholds at which we switch after the same time delay. And for that reason, we have plus and minus pulses with the same density. And this, of course, then, if we have a plus 1 volt and minus 1 volt with the same contribution, it averages to 0. Now, interesting is what happens here where we are at close to plus. There, if we switch to minus voltage, so if our 1-bit DAC is at minus, then we have a large difference to our input voltage. This means that the integration happens very fast, with a very steep slope. And after a very short time, we hit the threshold and then switch to the plus voltage. The plus voltage now is very close to our input voltage, which means the integration happens with a slope that is much, much shallower. So it takes a long time to reach the threshold. And for that reason, we stay for a long time here at the plus voltage. And like that, the sigma delta or delta sigma ADC generates a pulse train where the density of plus and minus values is proportional to our input signal. Yeah, so the same happens, for example, is visible here. Now here again at 0, we have equal mix of plus and minus. When the signal is small, Then when the DAC is at minus the reference voltage, we have a small voltage difference to our input. And so it takes long to integrate and hit the threshold. And for that reason, we stay long at the minus voltage here and only very shortly at the plus voltage. Okay, now this describes how a first order delta sigma ADC works. We can do, performance can be improved by quite a lot by adding more stages. Yeah, so what we had before is one difference, one delta, and one integrator, one sigma. And now you can take the output of that and put it through another stage. We build one more difference and one more delta, and then there's the integrator, and you feed the 1-bit DAC back into both of those stages. Now, what that does is it shifts the noise. So if we go back here, this signal, of course, contains a lot of noise. It does not look at all like our input signal. If we now increase the number of stages, what happens is that this noise is concentrated at high frequencies. And that's what's called noise shaping. So by designing many stages, 4 or 5 stages in an delta sigma modulator, as it is called, you can concentrate the noise at the high frequencies. And then the low pass filter that you have in a digital system can cut all the noise, all the digitization noise. And the nice signal, so the one peak that our sine wave has, then remains. And the difference of how clean this low frequency part of the signal looks like and how much noise there is in the high frequency part, this depends on the number of stages and how they are combined. And this is the like the art of calculating delta sigma ADCs, is to shift as much of the noise into high frequencies and to make the signal inside the pass band of the low pass filter as clean as possible. Yeah, so with that, with the low pass filter, you get rid of all the noise, and what you are left with is a nice and clean representation of your analog signal. And this is how audio signals, for example, are digitized if you want to have a high quality recording of a concert or high quality recording of data in physical experiments. Okay, that's it for today. Next time we will review performance of analog to digital and digital to analog converters, and then go into feedback control. Thank you very much for your attention. Thank you also for contributing in the quality control feedback of the lecture. We just got the results and they look very nice, so thank you for that as well. I will stay in the Zoom session now if there are questions, and please feel free to discuss.